Hello everyone. Today we are going to implement BERT using PyTorch from scratch. You can find the code in GitHub. I will put a link below, the GitHub link. And before we begin, I must say that this is an implementation from scratch, but we will not be implementing basic units such as attention layers or encoder layers, basic transformer units. If you want to see those implementations too, you should check the transformer implementations. Okay, we will take them from PyTorch modules. All right, so let's get into it. This is the BERT paper, okay, as you can see. Now let's look a bit to the paper and the architecture. Let's go to the model architecture. So we can see that it is based on the original implementation described in attention is all you need. So BERT is built on top of transformers. And the key thing that we want to look at here is it is encoder based. Okay. From the transformer model, we will only use and implement the encoder. We will discuss the decoder part. And they refer us to the annotated transformers, which I will show some examples to you from there. And we see some parameters here for base model and the large model. We will implement the base model. So this is for the architecture. And the next thing we want to look at is the embeddings. So to give the sentences, the queries to our model, we need a way to represent them. And this is what the embeddings are for. And actually in this paper, it is clearly illustrated. So let's say this is your sentence, okay. This is your tokenized sentence. And we will need three embeddings. First of all, the token embedding, which each one of them has a certain token. The second one is the segment embedding. It can take, from the paper, it only shows us the two values it can take, the A and the B values. But there is also a padding token, which it can take, the segment embedding. So we will treat it as it's going to take three, not just A and B, but A and B and the padding. And the position embeddings is basically the positions of the tokens. This is the general embedding part and the architecture. Okay, let's get into the implementation. Okay. Now we are here. We are in the BERT.py file, which we are going to put our code into. Okay, let's first create our main function, and we will start by assigning our parameters, which are, let me check, vocab size, number of segments. We will take these values from the paper, max length, embedding dimension, number of layers, attention heads. Let's put this also, and dropout. Okay, so first let's check vocabulary size by let's just put, okay. So as you can see, the vocabulary size is around 30,000 tokens. So we will just directly use it from the paper. Vocabulary size is 30,000. Okay, number of segments is about the segment embedding. And we mentioned that it shows only two, A and B, but we have actually three with the padding. So we will say it is 3. For the max length, we will go into the, it is maximum 512. So we will put that directly to 512. Now we will go into the architecture again to see the embedding dimension. Let's see, where is the architecture? Up. Yeah, here. We are going to implement the base version, and the embedding size is basically H, which goes as hidden size. Okay, 768. Number of layers basically means how many encoder layers we are going to stack top on each other. It is denoted by A, which is 12, okay. Number of self-attention heads. Sorry. Denoted as L, number of transformer blocks, number of encoder blocks, which is 12. Number of attention heads, that it is A, it is 12 again. And let's check the dropout. Dropout is 0.1 for all layers, so we use that just directly. Okay. So it is a good practice to put hyperparameters like this, so that you will have a consistent parameters throughout your model. Okay, let's see. Now we are going to start with the embedding part. Yeah, okay. Let's import the necessary modules. We are going to need Torch, and we are going to need the NN module. And let's create the BERT embedding class that takes NN module, and it will have the initial function initiation, class initiation. Okay, for embedding, we will need several parameters. We will need vocabulary size, number of segments, maximum length, embedding dimension, and dropout. Okay. And since it is based on PyTorch, let's initiate it like this. So as we discussed, we will have 3 embeddings. Okay, let's start with the token embedding. We will use PyTorch embeddings for this. And before we implement the embeddings, let's actually check the documentation of embedding. Okay, the first parameters take size of the dictionary of embedding, and the second is size of each vector, each embedding vector. So the thing about this, as you can see, they are all equal length. We are going to add them up. And for the number of embeddings, we will give different value to each of them. For example, for token embeddings, it will be the vocabulary size, since we can have number of vocabulary tokens, different tokens. For some segment embeddings, we will give number of segments, and for position embeddings, we will give maximum length. So it is the maximum it can have. Okay, so let's go. So for the token, as we discussed, we are going to give vocab size and embedding dimension. And for the segmentation embedding, we will give, for the segmentation, we will give number of segments and embedding dimension again. And for the position embedding, we will give embedding of max length and embedding dimension. So you may have a question here, and which is, why didn't we implement the positional encoding like this using sinus and cosinus? The reason for that is you can do it like that too. And on paper, it has an effect on performance, a decent effect. But in practice, we see that it is not that much, and it makes things slower. So it is usually preferred to omit it and just use the regular embeddings for the positional encoding too. But if you want to use like this, you can. It is a preference. But what I'm going to do is more popular. And yeah, this is more popular. Okay, let's put the dropout too. Again, we have the dropout value already, and we will give the positional inputs on the go. So what I mean by that is we will give value to every embedding here. But we can just hard code the positional embedding. So that's what I'm going to do. That's what I'm going to do. Okay, this is the initial of the embedding, and let's define the forward layer. We will take sequence for the token embedding, and we will take the segment for the segmentation embedding. For position length embedding, we already did it in the init part, hard coded it, and we will have a final embedding value, which is addition of every one of them. Like we see here, we add them up. Token embedding sequence plus segmentation embedding, which we will give segmentation self and positional embedding. Okay, and we will give positional input, which we did add up. And let's return this embedding value. Okay, so let's test it. Let's test if it works or not. For this, what we are going to do is we will create dummy tensors, which will act as our input. First, let's create sample sequence. We will use torch and the mint. The maximum value will be vocabulary size, and the size is obviously maximum length. Okay. We will do it for the segment, torch.randint, but the difference will be the highest value will be number of segments, and the size is same, maximum length. Okay. Now let's initialize the embedding, BERT embedding, vocabulary size, number of segments, maximum length, embedding dimension, and dropout. And we will have a resulting embedding tensor with forward of the embedding. We will feed sample sequence and sample segment. And as a result, let's print the shape of the embedding tensor. Let's make it tensor. Okay, embedding tensor. What I expect is this will have a shape 512, which is the maximum length, and the embedding dimension, which is 760. Okay, we made a typo here. This is dropout. Okay, let's try this again. Okay, another typo. Nope. So yeah, as you can see, 512 and 768. So our embedding works correct as we want it to be. Now let's get to the actual BERT. Okay. The same procedure. Take the module, init, take the vocab size. We will initiate the embeddings in it anyway, so we will take the same parameters. We take maximum length, take embedding dimension, take number of layers, take attention heads, and dropout. Again, since this is PyTorch, we'll do that. Okay, now we will first need the embedding, BERT embedding that we initiated like seconds ago. We will give it vocab size, number of segments, max length, embedding dimension, and dropout. Okay, so as we mentioned, this BERT is stack of encoder, transformer encoder layers. So we will create an encoder layer, which we can see here using this. We will have the embedding, number of heads, dimension of feed forward, which is 4 times of the embedding size, and dropout. We don't need the rest. Okay. So let's go. Encoder, layer, transformer, encoder, layer. We will have embedding dimension. We will have attention heads and embedding dimension multiplied by 4, like we just discussed. Now we are going to stack these up, encoder layers, and we can use transformer encoder for this from PyTorch. We will basically give the encoder layer instance and number of layers we want. Yeah, okay. Let's self that encoder block, that transformer encoder, which is parameters is our encoder layer and number of layers, which is 12. We just got it from the paper. Another way you can do it is you can just put all the 12 layers into a list and use a for loop in the forward part. But this is easier. Okay, and let's make the forward part. Again, we will have sequence and segments. First, we will use the embedding, and we will feed the embedding to the actual encoder block. Okay, and we just return the result. So let's test it too. Okay, let's create BERT. It will give it vocab size, number of segments, maximum length, embedding dimension, number of layers, attention heads, and dropout. Let's print the, let's take out and make it forward with, again, our sample sequence and sample segmentations. And let's check the size of the output, which again, as I expect, 512 and 768. Okay, this is for the embedding, and this is for the output of our BERT. So it is working. That is the BERT implementation. I will put the code in the description. You can check it out there. And thank you for listening.